Thank you. That's a very kind introduction. Could have been shorter. Yeah, so I would apologize, and it's great to see so many people here. Thank you for turning up. I apologize in advance for any coughing I do. 3 days of high steroids allow you to wake up at 3 a.m. and think, should I clean the garage out now or not? But they don't seem to suppress your cough completely. So I've still got a bit of a cough. So when Adele asked me to give a seminar, she says, well, try and find an intriguing title. And the only intriguing title I could think of was one from about 10 years ago, as was spotted by Peter, visitor here. So this is an old title about work. And the last time I gave a talk with this title was about 10 years ago. And the key message today will be that the title is out of date. Okay, so it talks about some work that I guess I've got a reputation for stealing other people's work, which I say in a positive light, of translation from other fields and taking ideas from one area to try and use them elsewhere. And this is an example of that. And what I want to talk about today is an update on some of the things that we did a number of years ago with a whole range of students. Now, the title is out of date because things have moved on. I think we can do more than that now. So just for your interest, this is the expanded title. When one of the things you don't know is the number of things you don't know, and also the things that you thought you knew you don't know. If by the end you can understand the title, I think we've actually been a success. So acknowledgements here to Jörg, Fabrizio, Oggy, and Andrew, who have been very influential in this work. I'll give more details about that later. Okay, so I'm a geophysicist, and I've worked a lot in the area of geophysical inversion, and that means across many types of data set, particularly geophysical data sets. Here's some classes of data that we have used in the past or looked at problems with: ambient noise surface wave tomography, magnetotelluric inversion of Earth structure, so broad scale, small scale, earthquake, tsunami floor displacement, and coupled finite fault. Airborne electromagnetic. These have all featured quite large. They're all different types of geophysical observable that we hope to constrain some aspect or some property of the Earth. Okay. Now, there is a book going of which slide you check out on. And I was going to start my slides, as I told someone earlier, at 10, try and get the number up. But hopefully we can stay with this. I've tried to gear this to a broad audience, but also to people who are interested in the detail of some of the work. So there'll be a bit of a mixture. So let's start off with art. Okay, so art, I think a nice art image. Anyone heard of a shadow sculpture? This is a shadow sculpture on the left here. It's called Wild Mood Swings. And what's the relevance of this? Well, really, it's a sort of an analogy of where we are in the geosciences. As I said, we collect data on or above the surface, or within the surface to some degree. We might bury some instrumentation. But we don't directly measure what we're interested in. Yeah, we measure something indirect. And that's where the indirect inference and inversion comes from. We would like to measure something directly and answer a question. I mean, I've often described inverse theory as an experiment gone wrong, because you can't control everything. You just have the data you have. To some extent, you can collect more data, but we can't see exactly the truth. We measure voltage mainly. Yeah, we typically usually measure voltage, and we calibrate that to something, a geophysical phenomena in this case, or it might be the age of a rock, and we want to make an inference about what happened in the past or what happened at depth, which is not accessible. And it's a bit like observing a shadow and trying to find what created the shadow. Yeah. And if I ask you what created the shadow, you might have some ideas, yeah, but you couldn't actually work out the answer exactly. You'd have to introduce information that I haven't provided to you. The shadow is just the data. What constructed it? Oh, let's play a test. Let's have a game. Who are the shadows of? Okay, we're going to have a vote. I'm going to present three couples, three artistic couples. They're all famous artists. And we're going to have a vote at the end as to which one do you think the shadows are of. And I won't name them yet. That's your couple A. Look at couple A. Extra points if you can name the couples later. Couple B. And couple C. Who votes couple A? No votes. Yeah. And there's a vote. Thank you again. Couple B. Some votes from couple B. Yeah. Yeah. Couple C. The mode is with couple C. Okay. Well, this is Wild Moving by Tim Noble and Sue Webster. And couple C is actually of Tim Noble and Sue Webster. Couple A, Diego Rivera, Frida Kahlo, famous artists from the 40s and 50s. B, Mapplethorpe and Smith, famous artists from the 60s, 70s, and modern day. Okay. But is that the end of it? Well, what have you done? You have used a conceptual model in your mind to say what created the shadow. This is what actually created the shadow. Okay, it is an extravagant solution and not one that you had in your imagination. At the same time, I tricked you. Yeah, I gave you three options. I forced a conceptual error on you. I gave you a categorization problem. I gave you three choices, but I didn't give you anywhere near what the correct choice was. Yeah, I forced you in a conceptual error. You picked one of the most likely, reasonable solutions. But the truth isn't that. And in the geosciences, the truth is never what we recover. What we recover is, at best, something close to the truth. It might be the Earth, it might be where an earthquake is, it might be what happened in the past in the mantle, based on conceptual assumptions. Okay, so when I say error, have fun with error, conceptual error. Okay, this is something I teach in the class I taught this year, and we've probably all done it in the past. Given a relationship between C, A plus B equals C, and I know my error in parameter A and parameter B, I can usually calculate the error in parameter C. I know you know how to do this. That's the answer. 90% of the class got that right when I taught it. That's parameter estimation. That's propagating errors in parameters from one thing to another. But what if there's a competing theory that relates A and B to C? For example, this one here. Now, this is another question I've given my class. What's the error in C given the errors in A and B? Well, you can use standard methods and get to the error is that, okay, under appropriate assumptions. But we have two competing theories here, both of which propagate different errors in parameters. So the notion of errors in unknowns is itself based on a conceptual understanding of the relationship between the inputs and the outputs. If your concept is wrong, if C isn't equal to AB, your error in C, even though you know your errors in A and B, will be wrong, yeah, because this relationship gives you a different answer from that one. Okay, am I making a big fuss about nothing? Do we really have competing theories when we analyze data in our field? You betcha. Okay, here's some examples. Where's Dave Heslop? Is he here? He's not here. He might be online. Dave Heslop introduced me to the phrase, "In GAD we trust." The GAD hypothesis for paleomagnetic data is often used to represent how the data relate to, with simplified physics, the properties of the Earth. And one sticks to a particular theory and one does some inference and works out your results based on that theory, but that's an assumption, yeah? Nice paper there by Andrew Valentine discussing the impact of arbitrary choices, typically around conceptual assumptions on what we get out of seismic imaging in that case, or inversion and inference generally. This is the scenario we have. The blue is something we're interested in, the Earth. So I work in seismology predominantly, so it might be the Earth, the seismic properties of the Earth. And we solve a deductive problem to predict from the Earth what predictions or what observations we might observe. We make a prediction, and we solve an inductive problem to take the observations to go back. And this is the difficult one, to go back. Yeah? So a forward problem and an inverse problem is my nomenclature. And what I'm talking about here are different types of forward problem, different assumptions, different physical assumptions. Why would we have different forward models? Because some are easier to solve, some are more convenient, some are the only ones we trust, and others we might not yet know about, or it may be difficult to use. But we may have competing assumptions. And we typically have to put our bets on one of them and stay with it. Here's competing assumptions in seismology, for example, a classic paper in 1999. This is a little anomaly here. These are ray paths of, it might be, well, it wouldn't be an X-ray. In this case, it's a seismic wave speed, similar to geometric optics, light. Yeah. Doing a source and receivers, measuring a cross borehole seismic experiment. Well, if we have some wave speed anomaly in the middle, which is slow, then rays will bend around it. They diffract, or they refract around. And if we have one that's fast, they actually shoot through. Okay, so the path that the energy travels depends upon the medium. We don't know the medium. Yeah? So if we make an assumption that a typical assumption that was made for many, many years, it's very convenient, is to simply say, oh, the ray paths are not affected by the medium. We know they actually are, but to a first approximation, they're not. That's one theory. And the other one might be to say, yes, they are affected. Let's take it into account. And seismologists have generally moved from one to the other, not because they thought they already know that ray bending is important, but simply because it becomes convenient that we can actually do it. Computation increases, it becomes easier, tools increase. So these choices are often a matter of what's convenient, what we can do, and okay, reasonable. We need to finish something in a particular time. But we make these choices not necessarily based on what the data want per se, but on what we can reasonably do. So this is classically called the model choice problem. Suppose we have a choice between two theories, A and B. We know B is better than A. But do we always choose B? No, we don't, because it might just be impractical, or it might not be that much better. Or how do we really know it's worth the effort? That's often the question. The choice may be as much practical as statistical. The question we're going to ask today as part of this is, when is it safer to use a simple theory? When are we allowed to make a conceptual error? Okay. Rounding off my introduction almost. So this is the work of Buser, a PhD student here, Buser Turunke, who submitted last year, or this year. That's from a paper. And this is a little experiment here. It's an X-ray style problem where we have X-rays passing through a medium very well, lots of rays passing through, and along those rays we measure essentially the absorbance of the X-rays. You could think of it as seismology, where we measure the travel time. The mass is the same, but these rays are straight. And this is the synthetic experiment where we know this is the model. Okay, this is the truth. So black means slow, I think, and light means fast. It's the other way around. Doesn't really matter. And we have these anomalies here, which are small and sharp. We also have a background field, which is smooth and on wavelength. Yeah. An inverse crime occurs when we test the algorithms like this, and we test them in exactly the right parameterization. Conditions are perfect, and we go, our algorithm works. Fantastic. But we don't actually know how best to represent the Earth. The way we represent the unknown is another conceptual assumption. conceptual error arises because we don't know the correct representation of the target. So here's the example of Bruce's work. If you represent this target, not in the correct way, but it's for using pixels, which is actually partly correct, not completely correct. Here's an example with the same size as pixels as in the true anomaly, part inverse prime, but we're allowed to remember we don't know where they exist. And we try and fit this using standard methods. We find a solution in a pixel basis. Take it from me, this is the best job we could do with the data, with the noise, etc., etc. But if we change that conceptual assumption, here I've used something called cosine basis, which is long wavelength. The one favors the short wavelength, one favors the long wavelength. We get a blurred image. And you can see they're both sort of right, but they're both actually wrong. These are conceptual errors that we're always forced into when we're trying to solve an inverse problem, because we're trying to represent the unknowns and we have to make some choices. So this is Bruce's work here that allows this particular attempt to try and allow both to be simultaneously included, and you can improve upon the image. And that's a spot algorithm, which has been published last year. But the point really is another type of conceptual error is the way we represent the target or represent the unknowns. We have to make some choices. So conceptual errors everywhere. Theory, model, also in data. Okay, so this is a famous image. It's an older one there by Andrew Schaefer, and it shows global tomographic models as a function of depth. These are different layers from different groups around the world. Typically, they're using not always surface waves or body waves. The data sets may differ between them. But it's only one Earth, but they're all seeing a slightly different Earth. Why are they seeing a different Earth? Are they stupid? Haven't they done it properly? No. The data sets are not that they overlap in these studies. Okay. They've made different choices. Choices around how they do their inversion of their data, of their processing. But also, you could even consider those as part of their assumptions. Their assumptions on how you represent the Earth, whether they're using full wave, what physics they're using, etc. How long and what type of algorithm. They've made conceptual, in the middle of those choices are conceptual assumptions. And as the assumptions change, the outputs change. So are we actually seeing the Earth? We're always not seeing the Earth. We're always seeing a property of the Earth. And this is the effect that happens in then trying to interpret this in terms of geodynamics, etc. And models differ considerably. And people look at these many studies over a long period of time, a lot of work to try and look at conceptual error or understand error. So how do we deal with conceptual uncertainty? I'm going to talk about three types of conceptual uncertainty as represented by the three colors here. This is in seismology, but really the concepts are broader. The orange one is the parameterization, your assumption, your conceptual assumptions about how you represent, in this case, the Earth, the seismic wave speed of the Earth. Different choices might be made. The blue one is the physics of the problem, or the chemistry, or the theory that you connect your target to your data. Different class of conceptual assumption. The green one I haven't mentioned, but it hangs around. Ryan mentioned it in his introduction, how we understand the noise processes in our data. Often that's another conceptual assumption. I haven't given an example of that. You could just loosely say it's a level of noise in the data. Sometimes we know it, sometimes we get it, sometimes it's a part of what we're trying to solve for. So a different type of conceptual assumption, and there may be others. You could probably think of others in your own problem. How do we deal with conceptual uncertainty? Is it just in our field that this occurs? No, of course not. Here's a nice little paper in hydrology. Conceptual model uncertainty, and I like this quote here in groundwater modeling. Uncertainty assessments in groundwater modeling applications typically attribute all sources of uncertainty in areas to parameters, A plus B equals C, and inputs, neglecting what may be the primary source of uncertainty, namely the errors in how you conceptualize the system, what assumptions you make to start the problem. So here is a clear indication that a suggestion that the conceptual errors may dominate a problem. Okay. So I always throw this one in because it's a fun quote. It's always about uncertainty. Chinese, a paraphrase of a Chinese proverb: to be uncertain is to be uncomfortable, but to be certain is to be ridiculous. And James Gleick's quote on Richard Feynman: he believed in the primacy of doubt, not as a blemish upon our ability to know, but as the essence of knowing. And I always put this in as a reminder that, you know, the modern word of uncertainty and error, taken outside of science, is often taken to mean a problem, a difficulty, a bad thing. Whereas in science, actually, as Feynman said, it is the essence of knowing something rather than a blemish on what we know. Okay, that's the preamble. This is actually the title of the seminar for the technically minded. A new approach to quantifying conceptual error in inversion. Matt, are you still with us? You've got a slide 13 if you're still with me. Okay, so there's a paper on this if people want any detail. Turns out that in the modern days to put things automatically on these open archives. I've already had people get in touch with me about this. The thing's not peer reviewed yet, but anyway, it's out there. Acknowledgements to Fabrizio and Oggi. My co-authors are Andrew and Jörg. Okay. So what I'm actually going to talk about and give you some examples are using data to choose between or combine competing conceptual assumptions in trying to make an inference. So deal with this problem from a different perspective, and I think a more formally appropriate perspective than has been done before. Typically, we make one conceptual assumption, we might do our analysis, get the answers. Do it with another one. If you're lucky, you do it more than one. Look at the results and go, okay. This is about trying to use the data to decide which or however many or what weights. Let's let the data vote on conceptual assumptions. I'm actually going to use a neglected, I would say it's neglected 30-old theory and give it a makeover. I'll just briefly introduce what the theory is, but it's by some other authors. We'll get to that slide. We're going to arrive at three types of, I think, new inversion algorithm. New for the geoscience. Always dangerous to say new in this game. Someone somewhere has done it. But new in the geosciences. And we're going to demonstrate utility for some numerical examples. And I'm going to show how these new ideas, I would argue, go beyond what we currently do in our field and have potential applications in different directions. Go beyond. Okay, so by way of the second introduction, there are two classes of approach to inference in the geosciences, or more generally. One is to build models through optimization, which is on the left here, and the other one is to sample models to get many ensembles of solutions. On the left here, this might be the fit to my data or fit to data and other things, and we're looking for a point on the plane, which is at the deepest well, the reddest down the hole there. And on the right, we might be sampling. It's a different framework where here we've got the highest density of samples in the region here, which has the best fit or the most likelihood, and we sample less elsewhere. I'm not going to go into the debate between which one is the right thing to do. Really, I'm a pragmatist. I've used both of these styles and I move between them when need be. Most of the talk will be on the right-hand side from now on. In fact, probably all of it from the right on. And it's called Bayesian sampling, Bayesian analysis. A posterior, a likelihood, and prior. If these don't mean anything to you, that's fine. The prior represents what we know before we collect our data. Often it could be an assumption as well. The likelihood is a more formal, how likely is the data given we have some model? How well does it fit? And the posterior is really what is the support of the data for any one model we might produce in our ensemble. So the density of these samples, hopefully where this is high, so we can then examine them. Safety in numbers, essentially. And what we use to do that, the standard engine for 50 years or so, I've dropped my image of the Monte Carlo casino, but it's the Monte Carlo method, the Markov chain Monte Carlo method. Now, here's a simple little animation. The pluses are the hills, the negatives are the lows. So this is high probability for a model, high density, low. And Markov chains work like this. This is actually a Markov chain walking around trying to sample things. It's sort of randomized. I'll give a bit of detail later, but it's attracted to the regions of goodness, regions where we want the model to go. This is an example, 2-parameter problem. And this is the heat map of where it's been. And hopefully by the time this thing's done, it won't be perfect, but it will sort of try and map out this function. And we therefore have all of these models. Everywhere the red dot's gone, we have a solution. They're not equal everywhere. They're concentrated where we would like a solution to be, less concentrated elsewhere. We're going to analyze all of them. And that's the sort of get the idea that in a very simple case here, we've got high densities there, higher here, there's a valley in between. And that's a Markov chain. Enough of that. Here's another one. Okay, so this is work of Rhys Hawkins, who was a PhD student and a postdoc here, and applying the same sorts of ideas to transdimensional Markov chains. Now, transdimensional is one where the number of unknowns is one of the things you don't know. And here we're fitting this data. This is an old slide, and we're trying to we're fitting it with different orders of polynomials, straight line, constant, quadratic, cubic. This is going to be the order of the polynomial. This is the final state, and you'll see the same sort of thing walk through. This is a Markov chain which is changing the number of unknowns as we run. And you can see these jumps occurring as it changes and it settles down. This is the number of times it visits each state. So polynomial of the order 0 is a constant. Really not visiting that because it's a poor fit. It likes a nice first order polynomial, which is a straight line. It sort of favors 30% to a quadratic, not much for a cubic. And the whole point of these things is it follows certain rules. It's an extension of fixed dimensional Markov chains to trans-dimensional. We're varying the number of unknowns. And you can see it has this thing called natural parsimony, and it doesn't just give you the best fit. These have the best actual fit to the data, but it favors lower ones because they are essentially more supported in this paradigm. And the truth here is that it is actually a first order polynomial. But the data don't uniquely say it must be first order. It could be second order, it could be third, but it gives you a vote, essentially. Okay, so trans-D, which is the existing theory, at least for the last 20 years in the geosciences, has been quite popular. This is a slide, a Web of Science data I got from about April this year. Since 2000, since the work of Malamverno, who really introduced this into the geosciences, Alberto Malamverno, there have been about, at this then, 214 publications, about 5,000 citations. If this was a person, they'd have an H index of 36, that's higher than. It's not a person, it's a topic. And if you cut out, in my search, if you cut out geoscience in the title of the papers, you get sort of 1,200 papers in the computation statistics. This is a popular activity that's grown over 20, 25 years, really based around elegant work by Peter Green, but also people that often get forgotten are Geyer and Muller, who did work slightly earlier, which is a bit more of a specialized version of this, which many people actually use rather than the Green algorithm. So give a shout out to them. But so this has been a very popular endeavor in the geosciences. And as I mentioned, trans-D is all about jumping, coming back, jumping, trying a model, coming back, and following a prescribed set of rules. I'm not going to go into detail. It's a thing called the Metropolis Hastings, Hastings 73, Metropolis 54, Green 95, that allow you to jump around and sample models with different dimensions and have it all worked out very nicely, and you get a parsimonious solution. And we've profited from this over a large period of time. And now I'm returning to the slide I had at the beginning, because all of these studies are actually trans-dimensional studies, and they're all by students and postdocs of this school. there's a bit of a plug for RSES, because the school was one of the leaders in promoting this idea. And there's people in the room, one of them, who was an early pioneer of this, with many of our postdocs and students, Tom Bowden particularly, Ross Brody at GA now, just retired. You have one of your students already retired. Terrible. Young Detmer is at Calgary. They're all transdimensional studies, and it's become very popular because they have nice properties. You can have the degrees of freedom varying in the problem. This is Mallory Young's work with Hivoya and co. on the core mantle boundary. Is a true model, a synthetic test. That's a transdimensional recovery of a checkerboard, and that's the linear inversion, the best they could do, etc. Really put in to show the diversity of applications. This is a nice little animation. Fabrizio actually did it this afternoon. Thank you for jumping on the bandwagon there. Thank you very much for responding. The point of this slide is, that's working. So this is one application where we use the trans-D stuff to vary a parameterization in a surface wave study of Australia. This is by Thomas Bowden, where the number of cells themselves, how you represent the Earth, changes, and it adapts to the data using these trans-dimensional ideas. I put it in there to sort of picture what goes on. The number of cells goes up, they can go down. It's driven by the data. And this became very popular as an imaging technique. But just one bit of math at the bottom there, that's only one of the many terms you have to derive. The point of this is that to get this to work, you have to derive the appropriate, what they call balance condition. And to be fair, it's tricky. Yeah. Thomas pulled his hair out for 3 months trying to get this right. And we got it right. We thought we got it right. We go backwards, forwards. Even though we know the overriding theory, to implement it for any one problem is difficult. It requires derivation of the appropriate conditions. And that's my point here. That's difficult. And as soon as we change the problem, you have to do it again. Or at least most problems, if you want to change it from this to a 1D Earth model or some other scenario, typically you have to do the math again. Even though what you're trying to implement is the same, the detail is bespoke to the problem. Which is my first point here. Trans-D, a problem with trans-D is that it's bespoke. Okay, now if any of you were in the talk on Friday where Fabrizio showed his code, his Bayes Bay code, which is a beautiful code, which allows you to implement trans-D across a range of problems, but it's still within a particular class. He's generalized that. If I want to swap to a completely different style of problem, we have to often derive what you're implementing again. So to some extent, you can make these things flexible. But if, for example, I represent my 2D model by pixels, let's say as I did earlier, and I want to change it to basis functions like cosines, it's almost impossible to do this with trans-D. And that's with reversible jump trans-D, because it requires certain mathematics that relate one parameterization to another, depends upon the detail of the problem. It is not automatic. A second disadvantage is there has been 30, 40 plus years of development of Monte Carlo algorithms, not by geoscientists, by the real people, the Bayesian statisticians that derive all of these great methods. There's code out there, you can do it quite easily now, but most trans-D cannot take advantage of any of that, okay, because it's bespoke to the problem. Typically, it was a lot of work to put these packages in. In fact, you can't really do it for trans-D because it has to move across different numbers of unknowns. So there are technical reasons why they're unfriendly to a vast array of resources we can't take advantage of. And as a consequence, there's a limited number of applications, even though I showed you quite a few in our field. There's a lot of cooling up time, a lot of work required to get that to even go. Peter Green realized back in 1995 that the real ideal would be having automatic trans-D sampler. And by that, they mean having your essentially algorithm over here independent of the details of the problem over here to be able to make them work, plug and play, a bit of Lego. And he did some work along this line, but really said that they don't really exist. That would be the goal. Okay, so I want to now expand and go back to the conceptual issue. Oops. Different types of ensemble. So I've talked about a fixed dimensional ensemble. So here's like a layered Earth model where we're changing the parameters. We might change the width. That's an example of an ensemble inversion on a physical problem where we're only varying in depth. But our numbers of unknowns are fixed here. It's 3. The trans-dimensional has variable numbers of unknowns. So layers are added and subtracted in this example. But I'm going to introduce this concept of a trans-conceptual ensemble as ones where the nature of the model changes as well. Here we've got smooth variations with depth. Here we've got a fork, an angled fork. Here we've got undulations in the surface. The trans-conceptual incorporates the trans-dimensional, because this is just a subset of this, just as this is a subset of this. So, but trans-conceptual is actually allows you to, or at least the definition of it is broader in that sense. By trans-conceptual sampling, I mean we can think of ourselves having different states. Here's my little round bubbles here, and I make assumptions in each state. My assumptions might be the number of unknowns in my problem, how I represent the Earth, what's my noise in my data, what's my physics of my forward model. Remember I said at the beginning, we often fix those completely. Well, I make one set of assumptions here, a different set of assumptions here, and a different set here. And what I'm going to do is describe trans-C or trans-conceptual sampling as ones that can walk between these different states and let the data try and tell you not just like which is the best state, but really how you draw your inferences by combining them all together. So just as trans-dimensional work really vary only the number of unknowns here, the top line, trans-conceptual I'm defining as something which can vary anything. And the reason this will work is because of we'll get to that. Okay, so again, the difference between fixed D is trying to find a posterior, a Bayesian posterior like this, a probability distribution of the things we're interested in. Trans-D varies the number of unknowns as well. And trans-C will vary and let the data vote on the states as well. So one set of assumptions here, another set here. What are my limits of my assumptions? Anything you want. Okay, so check out if you don't want to know the details. But the paper that this all comes from is by Carlin and Tibb in 1995, who proposed an alternate way of looking at these trans-dimensional problems. And what they did was, to cut a long story short, was really just to make a larger problem out of a whole series of smaller problems. They simply said, do you know that if you formulate the problem this way, and I'm giving it by the box here, if my states have numbers, and this is state 1, state 2, I can concatenate all my unknowns together. I might have 5 unknowns in one, 6 unknowns, put them all together, and just say I've got them all simultaneously. We call that the product space. And what they showed was, with a bit of sleight of hand and some beautiful sleight of hand, you can introduce these things called pseudo priors, they called them. Let's not worry about the details. And you can sample a fixed dimensional problem and solve a trans-dimensional problem, because the solution of the trans-dimensional problem essentially lies within the samples of the fixed dimensional problem. And they proved this. Okay? I'm asking you to take my word for it. It occurs to me, it took me 2 years to really understand and exploit this. It's asking too much of you to get it in 45 minutes. I accept that. Okay. But this idea essentially solved exactly the same problem as Peter Green's algorithm in 95, but it was really fell away in terms of take up, because Green's idea was really quite elegant and efficient. Okay, so everyone really worked with green, and green became very famous already. But the older idea here actually has some advantages, I would argue, and we can revisit it. And the reason it has some advantages is that it embeds this problem into a fixed dimensional space. Remember what I said, there's 30 years of samplers on fixed dimensional. We could apply them directly to this problem, take the output, sieve them, and we've got the answer to a trans-D problem. So we can convert a difficult problem into a simpler problem, use great tools, and come back. There will be a question of efficiency. You can see the problem with this already is that we're actually going to do it in a much larger dimensional space, larger numbers of unknowns, and that is tricky. But in theory, this will work, and I'm going to demonstrate that it works. And then I'm going to show 3 different detailed. Turns out that this is partly our contribution, or that this idea boils down into 3 different samplers, 3 different tools that we can use in slightly different situations. I'm going to briefly mention. One I'm calling the product space sampler, which is exactly what I just said. You embed the problem in a big space, you solve the big one, you filter the results. We can take advantage of many, many algorithms that are out there. We can use modern packages of HPC, which we couldn't really do with the trans-D stuff. Okay, I can simply provide the problem. These are automatic. Run the advanced tools, go and make a cup of tea. The downside is that the number of unknowns grows, okay, and that's a problem. These things would be harder to implement if the number of unknowns gets bigger. It just takes forever. We use NCI for the whole year. We might get to an answer. So they're not very practical when the problem gets bigger. The details of that are in this paper. Okay, but it turns out, and it was immediately understood by Hastie, Green, and Godsill, that actually you didn't even really need to do that. Okay, the product space idea actually drops away very quickly. If you look at the theory, it turns out you can derive from it, which I'm calling the pseudo-prior sampler, something very similar to Peter Green's algorithm of 1995, with the same essentially workload, the same constraints. So you can do things much more efficiently. The difference being that you carry forward this idea of not having to, and this is the key technical point, which will mean something to some people, is that you do not have to transform parameters from one type of model to another, okay? Because they're in there simultaneously, effectively. So models are changing in state 1 or in state 2. They're not actually moving between the states. And that's in Green's algorithm, the moving between the states is the difficult bit that makes it bespoke, okay? And elegant and fast, but this was avoided. In some sense, it's a cruder version. But in doing so, it introduces these things called pseudo-priors. I won't go through the maths, but it works. So the point about the number 2 algorithm is the workload and requirements are very similar to the reversible chunk. And here's the third one, which I like particularly, because it turns out you can reduce even the second one down to something very, very simple. And I'll call that the ensemble sampler. The ensemble sampler is one where all you really need to do, and the algorithm follows, all you really need to do is sample each space independently using 30 years of great codes out there that we can pull in. I can do that one on Tuesday in Amsterdam, this one on Wednesday in Buenos Aires, completely independently. And what this allows you to do is mix the states and work out exactly the same trans-dimensional output. You can get the same output from fixed dimensional states. Point being that this is actually extremely simple to implement because you've only got one unknown and it's just a pointer. How many times does the data want to go to state 1, state 2, state 3? So now I've got one unknown to solve for if I've done the pre-work of doing each state independently, which I can do with many, many tools on parallel machines. So this scales quite nicely, is the point. Okay, so I've briefly introduced the 3 ideas. They're all the features, who cares? Okay. We're going to go to an example. Simple example. I'll just finish with some examples in the next 130 slides. Here's my 3 samplers working on a trivial problem. I'm just sampling a Gaussian in 3 dimensions, 5 dimensions, and 10 dimensions. These are 32 chains. You'd have to take it on trust that I've implemented this properly. Here's the product space sampler. It hasn't really converged here. This is the pseudo sampler, which is converged better. This is the ensemble sampler, which is converged quicker. Here are the three outputs. I've actually forced these three Gaussians to have different weights, essentially. So, and I know the answer. The answer is the blue dot, the yellow dot, the green dot. And I'm just getting some confidence up that all three of these actually are in the right path. They're not biased. They're not going somewhere else. They're calculating essentially the integral of the state. But that's the weight that the data would want between any of the three states, 3D, 5D. So it's 10 parameters, 5 parameters, 3 parameters. But you can get the idea that the truth here is the green and the others are the estimates of the three samplers. So they all seem to be converging in this trivial little simple problem. Now, I said that the trans C idea has the trans D as a subset. So in theory, then, if we can implement this trans C idea, we should be able to solve any trans D problem. So we should be able to compare to previous work that is actually implemented and done all the hard work. So here's Ross Brody's work here. This is recalculated by Jörg. Here is an airborne EM study. It's one fiducial of the Century deposit data set. I think, no, maybe I got that wrong. I need to dig that out. So it's airborne EM. So this is the resistivity of the Earth in the first 500 meters. This is the result from 2012 by Brody at one particular location. And here's a trans D result where he's varying the number of layers and the properties of the layers to try and look at the profile of the Earth down to 500 meters. And he gets this result. This is a real data example. And here, because we're varying the number of layers, the trans D can tell you how likely there is a layer discontinuity in your model. And that's his result. And this is the result of the trans C result with the ensemble sampler. So you can see it's quite smooth because it's only a one parameter problem once you've done it. So you can actually do billions and millions, make it nice and smooth. And I would argue those two are pretty much the same. Yeah, that the blue there is the medium, just for comparisons, the density of all of the 100,000 or so models. So here's some evidence that we can reproduce a trans D problem when it's a trans D problem. Okay, so I want to finish off by showing a problem I think that trans D cannot solve at all, which is this one. So varying the parameterization. I'm going to show a tomography problem, this is a synthetic problem, where the unknowns here are pixelated. So here's my model, it's pixels, and I'm looking for the wave speed in the pixels. But I'm also going to compare that to a second class, which are cosine functions like this. So these are smooth, as we showed earlier. These are sharp and pixels. Getting trans D to work in this, you could never really, it would be a lot of work to try and even understand. In theory, it's possible how you move from one to the other. That's the technical problem. Pixels and cosines, okay, of different wavelengths. And I'm also going to allow the physics to vary. We talked about straight rays going through our model and curved rays. So I'm going to have some straight ray states and curved rays. I'm going to change the physics. I'm going to find states with different classes of parameterization and different physics. See what the data say. So here's the problem. It's a cross borehole. Again, some sources and receivers, paths crossing two anomaly model. I have not really committed an inverse crime here because this is my true model. We're testing slow and fast anomalies. They're two Gaussians added together. And the assumptions I'm making is they're either pixel or cosine, and I want the data to tell me which. Pixels with different numbers of cells, cosines with different wavelengths, essentially. And I'm going to create 16 states in total. I'm going to have four of these, and multiply by 2 because I'm going to have the physics changing from ray theory to ray bending. The 2 types of physics, 8 types of parameterization, all different conceptual assumptions. Normally I'd fix them on one of those. And I'm going to try and sample across the states. Okay, so here, just to show you that things have worked, I've sampled the prior of Gaussian, pretty similar to the one before. We'll jump over. And here are my results. Okay, so this is a test against pixel models. Even doing this is a little bit tricky, even with trans D. we're changing the number of the size of the grid. The red dot refers to the truth, the one that the data was generated in this case. And this is a histogram across each state of the final state. For two of the samplers, the ensemble sampler, which I'd say is fast and simple. The pseudo sampler is the middle one. The product space sampler is probably too big for that. Yeah, product space sampler is not really going to work in any reasonable problem. So I can only get the first two to work, or the second two to work here. But you can see that the sampler, here's all the details, is almost 100% in the correct parameterization, both blue and pink, both samplers. You can see it here. This one is using ray theory. There's no visits to ray theory, straight ray theory. This one's using ray bending. Everyone's gone to visit ray bending. Ray bending was the correct physics used to generate the data in this problem. We've done bent rays. But the data in this case can decide that the straight ray approximation is just not good enough. We prefer the bent ray approximation. The parameterization we prefer is the 24 pixels, so the 6x4, and the red dot is at the 6x4. As we change the true parameterization, the posterior mass has followed it and always got in the correct physics. So this one's looking good. We can solve multi-physics, multi-pixel parameterization. It's the same thing for the smooth model. Multiple physics, multiple parameterizations. Some things are not so hunky-dory here now. The grey is the product space sampler. It basically hasn't converged. It's a bit rubbish. But the other two have converged to the correct answer. We've got a little bit of leakage here in this one. And this is all about how long you've run the things for. Have you actually got consistency? But you can see the red dot is where the posterior peak is. So again, it's picked out the correct physics and been able to do something similar with the cosines, a smooth model. And the final example I'll show you there is that it's actually mixing these states. Now, I would not believe you could do this with trans-D, but we're mixing pixel states with cosine states. Very difficult to do, but it's actually in principle no problem for a trans-C approach. And we get, again, the red dot. We've got a bit of leakage in the ensemble sampler here. It hasn't been run long enough. Okay, so it is encouraging. These are the three results in the paper. My last few slides, I said we introduced this thing called pseudo prior. Now, everything will depend upon the pseudo prior. What is the pseudo prior? It is simply just a normalized probability distribution in the space. That's all you really need for it. How do we generate it? You can make it up. You can use some fitting processes to calculate it. In the paper, I've used one or other of these in each of those examples, but there really is a potential here to bring in machine learning into this process, because machine learning, the field of machine learning, have you ever heard of it? It's grown. And one of the things it does promise to do is build things exactly what the pseudo prior is, i.e. generate probability distribution. So there's a lot of opportunity to make these things grow and be more efficient by bringing in the notion of machine learning tools into this idea. I've just used very simple approaches in this paper so far. Okay, I'll finish with my final slide. So current trans-D samplers have restricted applicability. Because they only are practical in in special cases when you compare it to conceptual sampling. Current methods do not lend themselves to generic software, whereas essentially the product space sampler, which is not going to be very efficient, but the ensemble sampler can both make use of 30 years of work of others. We're introducing applications to improve model recovery. So you don't actually have to just find the best parameterization. You can look at the Earth based on what the data votes for all of them. You don't actually just have to choose the best. Yeah, each one represents an output. You can sum or average the outputs and look at the Earth. Or you could use it to justify your favorite simple theory, i.e. the GAD. In GAD we trust. Why should we trust it? Maybe we can work out that we shouldn't trust it, or we can verify we should trust it. So all three of these algorithms that we've described are provably convergent, performed well in initial trials. It's just started this. They won't be equally successful in all situations. I even showed that in my examples here. And there's a lot of potential to advance priors in this key area of research. So I think we've expanded the range of problems that can be solved. We've also, by just as a byproduct, generated an automatic trans-D sampler, because as I said, none of this stuff depends upon the mathematical details. As long as you have a pseudo prior, the things will converge, or they will converge in a theoretical limit. So let the data decide on whether your assumptions are supported. I'll leave it there. Thank you.
Okay, so it looks like there's no convener, so I'll just take a couple of questions. It could have been a little bit shorter. So I'll take a couple of questions from Mark.
I just cut out 30 slides.
Yes, Virginia.
Thank you, Michael, for the wonderful talk. I have one general question. When you mentioned we can do like some independent sampling for some fixed dimension problem, and then go back to estimate the trans-dimensional problem.
Yeah.
So do you mean like I already have the fixed dimension problem? I already have the result. Do I need to rerun the sampling, or I just have this one to make it use the current?
So the quality of the output will be dependent on the quality input. GIGO. If your samples are good enough in your fixed dimensional space, then you have to do nothing. That's what we took from Ross Brody's study. I didn't actually generate those. Someone else generated them, and I took their sample.
Yeah.
So yes, so you can make use of previous studies if you have the outputs of previous studies. That's right.
Thank you.
Yeah, there's one question about
Yeah, thanks for the interesting and detailed talk.
It comes to the tough question.
It's a non-technical question, actually. That was curious to hear from you how you got to study in the first place the Carling and paper from 1995. And what led you there?
You know, I can't even remember. To be honest, I can't. Fast forward to the end. The ensemble sample that you just asked about was the desire. The question was, does such a thing exist? I wasn't really clear if it did. And that paper suggested it might. And then we sort of walked through a long pathway from beginning to end. But it's probably just serendipity, as many of these things are.
Yeah.
May I make a comment rather than a question? I like your last line on the conclusions here, which I think has been a theme of so much of your work over decades, Malcolm. And I think it's a reminder to all of us, to myself included, to avoid getting too committed to models that represent a certain set of data that we've gathered in the laboratory or the field. It's a plea for open-mindedness.
Yeah.
It's very well.
Great, and that's a great way to end this conversation. And I'm sure people need a bit more time to digest this, and then let's come back.
You got 1 year, 11 months,
Talk with Malcolm. So thanks again very much, and we have a tea after this. So please give
Thank you for coming. Thank you.